Yeah. Hello, everyone. I'm Bojin Liu, and this is a joint work with my advisor, Jeff Huang from Texas A&M University. So initially, thanks a lot to my professor. Yeah. So concurrency bugs usually happens. They are really hard to detect and debug. So the most common types of concurrency problems are data races and deadlocks, which always cause serious problems. So there are a variety of existing classic techniques that works on this problem, but most of them are too late because they are designed for the late phases of the software development. So at that time, fixing a bug could be very expensive, and moreover, it might be too difficult for a developer to understand a specific reported bug because he may already forgot the coding context. Moreover, at this time, those techniques are working on to analyze the whole program, which makes these techniques harder to scale. So can we do better on this? So can we detect those bugs in the early stage so we can solve the problem as early as possible? So the answer is yes. ECHO, which is our group's prior work, targets as the programming phase. So after an initial whole program detection, users may introduce small but frequent code changes into their program. So taking those changes as input, ECHO performs incremental detections to infer the newly introduced bugs and report the bugs to users as early as possible. So for their experiment, for 92% of the tested statements, they can achieve the incremental detection within 0.1 seconds, which is really fast. So can these techniques work for large programs, have the same scalability? So we have performed the evaluation on some large benchmarks. So the whole program detection always requires like 6 hours. And even though ECHO is already really fast, so for some worst cases, their incremental detection, for example, the incremental pointer analysis and incremental static happens before analysis requires around half an hour and 2 hours to complete for one update, which is far from instant. So that's why we provide this D4. So a fast static concurrency bug detection framework. So it can achieve a significant performance improvement over ECHO. So no matter is the performance of the incremental pointer analysis or incremental happens before analysis. So we'll show more data later. So how do we achieve those scalabilities? So there are two key insights in our techniques. One is that we utilize the incremental code changes. The other is, I'll tell you later, okay? So taking the incremental, a set of statement changes as input, so we develop a novel pointer analysis, a static happens before analysis, and we perform detection only on those change affected parts and return the newly bugs to the user. So all of the three components are incremental that only analyze the change affected part. Moreover, the three components can be further parallelized to further improve the performance. So that's the other key insight in our technique. So we adopt a client-server mode to send the changes to a server, a high-performance computer. And next, I'll introduce the three components one by one. So firstly, the incremental pointer analysis, which is the key component and the key contribution of our work. So it determines the difference in points to set for those change-affected variables. The code changes include statement addition and statement deletion. for a modified statement, we can take it as a deletion of the old statement and the addition of the new statement. So for addition, it's simple. We can follow the on-the-fly Anderson's pointer analysis. But for deletion, it's a little bit harder because we need to remove all the facts that are no longer reachable from the existing statement. So before I introduce our technique, I would like to introduce two existing incremental algorithms to handle the deletion. So one is the reset recompute algorithm. So we take the previous deletion as an example. So here, after removing the age on the peg on the pointer assignment graph, so it will reset all the points to the set of y and w, and then extract all the constraints related to those changes and recompute the points to the set. So its performance bottlenecks is that it involves some redundant computation. For example, here, the w, the points to the set of w, has not changed before and after the statement deletion. So the other algorithm is a reachability-based algorithm. So for the same example, after removing the age, it will perform a graph reachability check to find out a path from the object node to the y node and check the w node later. So even though there's no redundant recomputation here, the graph reachability check could be really expensive for large programs. So to overcome those performance bottlenecks, we developed our incremental pointer analysis. So the key insight here is that we discovered some local neighboring properties. So I firstly introduce some concept. So for a node R in a peg, we define O as its incoming neighbor and define Q as its outgoing neighbor. So if we want to incrementally update the peg, which is currently a cyclic peg, it is sufficient to check the local neighbors of the nodes corresponding to the changed statements. So for the detail of those properties, please refer to our paper. Right now, I'll use an example to explain how our algorithms works. So after removing the statement, initially we'll remove the age, and then we perform the analysis on y. So we check all the incoming neighbors of y, which is z currently. So since in these points to set, it includes O2. So according to the transitivity of a peg graph, so we can know that O1 should no longer belongs to the points to set of y, and we remove it. So later we propagate the change of points to set of y to all the outgoing neighbors of y, which is w right now. So we restart the analysis on w. So we check all its incoming neighbors. So currently it's x and y. So since O1 is in points to set of x and O2 is in points to set of y here, so we can know that we don't need to touch anything in points to set of w. So since w is the only outgoing neighbor of y, so the whole update process has been complete and we can just exit. But the above example is really the simplest case. So what if there are multiple age changes in the program, in one commit change? So we solve only one ages in each fixed point iteration here to guarantee the correctness. But all the previous properties and the algorithms are based on a cyclic peg. So what if there are cycles? So we performed a incremental SSC detection to guarantee that after each age change, the peg is always a cyclic. So next, I'll talk about how we parallel this process, the incremental process. So the key insight here is a change consistency property. So take the graph and the deletion as an example. So for an age addition or deletion, So if the change can propagate to a node from multiple incoming neighbors, the changes applied to the points, corresponding points to set will always be the same. So we'll continue with the example here. So for here, the change can be propagated to y from the purple path and the orange path. So right now, we parallel the propagation on the two paths. So we cannot determine which path can reach y first. So right now, let's assume the purple path can reach to y first. So we performed our previous analysis on this. We removed O1 from points to set of P, and then from Q, and right now it reaches to Y. So currently we check all the incoming neighbor of Y, and then we need to remove O1 from points to set Y, since we know that no one can provide the O1 here. And then we schedule an update for W. So later, the propagation from the orange path reaches to Y. So at this time, since O1 has already been removed from points to set of Y, so the process just complete. We don't need to touch it. So this time, let's assume the change from the orange path reaches to Y first. So at this time, we check the incoming neighbor. We won't touch O1 since it's the points to set of Q can provide O1 here. So later, the propagation from the purple path reaches to Y, and at this time, we need to remove O1 since the points to set of Q has changed. So finally, we schedule the update for W here. So as we can see that in both scenarios, the finalized points to set of Y and W are always the same. So next, I'll talk about our static happens before analysis. So before that, I'll introduce our existing work in Echo. So the graph constructs per thread sequential traces. So we can see that the highlighted nodes in the graph are repetitively represented for the statement in the method. So imagine we have a really large program, the graph can be really large. For a statement deletion, we need to localize all the corresponding nodes in the graph and remove them. This makes the incremental update becomes expensive. So to make it cheaper, we introduced the concept of sub-SHB graph. So this is a unique graph for each threads and methods. And it has a thread ID field to record the thread that invoked this method. So with this representation, we have no repetitive nodes in the graph, and we have a compact graph with fast construction and incremental update. So we use the same example. So initially, we create a subgraph for the main thread, and for a thread start node, for the thread start statement, we create a subgraph for T1, and continuously for a invocation, for a method invocation on M1, we create a subgraph for M1, and continue, and we see another thread start, and create its subgraph for T2. And right now, we see the same method invocation on M1 again. So at this time, we just add an edge from the call node to the subgraph of M1 and update its thread ID field so that we avoid to repetitively traverse those statements. And we continue until there's no statement need to be processed. So what if I have add a method invocation here? So what I need to do is just add a corresponding call node in the subgraph, add an edge, and update its thread ID field. So for a statement deletion, we only need to locate the unique corresponding node in the subgraph and remove it. So the update process becomes more efficient. So since statements in different threads and methods are independent, So we can parallel the subgraph construction and the incremental updates in different subgraphs. So for concurrency bug detection, we focus on a data race detection and deadlock detection. So for data races detections, we adopt the same algorithm in Echo. So we check the happens before relations of common memory accesses and in the new SHB graph. So if there's no happens before relation, we will report it as a race. So we maintain a lock-dependency graph for the whole program, deadlock detection, and incremental detection. So when we traverse the statement, when we see a synchronization on M and points to set of M includes O1, so we created a lock node in our graph, and we continuously create the node. We add an age to indicate their order, with a label T1 to indicate that the operations are invoked by T1. And another time when we see another synchronization on P, where P's points to set has O2, so we will locate the corresponding lock node in the graph and add an age with the new label. So what if I insert some synchronizations? So what we need to do is to create its corresponding lock node if it's absent, and locate the lock node happens right before and after it, and add ages with labels to indicate their new relations. For deletions, we located the lock node and removed its corresponding related ages. So for incremental detection, we try to find a cycle in which ages are labeled with different thread IDs. So at that time, we check the happens before relation for those lock nodes. If there's no such relation, we just report a deadlock. So D4 is implemented on top of Vala and Akka for Java programs. So we have a client-server mode for evaluation, and we have a Eclipse plugin for users to help with their debugging. So besides that, our pointer analysis has been adopted by Vala. So we evaluate 14 benchmarks in decouple. So we perform the whole program detection as the first time, and then we deleted one statement to perform our incremental analysis, and then we add the statement back to perform our analysis again. So to evaluate the performance, we ran our analysis on one single thread and 48 threads to compare with the existing techniques and compare the result. So here we only show the result for those worst cases in statement deletion for the pointer analysis. So as we can see that we have a lot of performance improvement. So here is a summary of our incremental pointer analysis. So the sequential version has achieved a 300 times speed up over the existing incremental techniques we introduced. And our parallel version further improved the performance. So this is a summary of our parallel incremental concurrency bug detection, so that we can achieve the same speed as Echo for large programs. So in summary, we have introduced a design and a development for a faster framework for concurrency debugging, which is D4. So we also provided 2 fundamental static techniques. And with those techniques, D4 can pinpoint bugs within around 0.1 seconds on average for each change. And we achieved like around 1,000 times speed up, faster than the exhaustive and incremental analysis. So yeah, thank you. And questions?
Questions?
Hi.
Hi.
This is Eric Bodden from Paderborn University. Nice work.
Yeah, thank you.
So I was wondering, in your work, do you also persist the intermediate analysis information somehow, so that if you as a developer, you close a project and you open it again later, that the information is still there, or do you all keep that in memory?
Yeah, so currently we don't, but we are trying to work on a put those things on cloud, on server, so that we can have some record for each project for users. So it would be more convenient for them to use these tools. Yeah.
Because in my experience, there's also a cost involved in persisting that, right?
Yeah, sure.
And that might be interesting to measure.
Yeah.
Okay.
Thank you.
Thanks.
Hello. So in given the fact that you are abstracting the analysis result from multiple contexts and multiple thread invocations, I assume that your analysis is context and thread insensitive, right?
Excuse me.
So your analysis is context and thread insensitive, right?
It's context insensitive, field sensitive, part of object sensitive, path insensitive. Yeah.
I see. So how that affects the? I'm sorry. How that affects the precision and how much ratio your all-ums are true?
How much races?
I mean the precision. How your precision affects.
So we compare with the whole program analysis result. So since we adopted the same algorithm for race detection in Echo, so we only compare with their results. So we have the same. We detect the same races. Yeah.
Right. I think this is a similar question, but does your technique ever miss races that are in the program, and does it ever report races that are not actually races?
Yeah, we have false positives since we are doing static analysis, so we can avoid false positives. Yeah, but
and how many false positives do you get roughly?
It's hard to say since those programs are really large. Yeah, so we spend some time to manually check those bugs and compare with the database. Bug databases already exist. We can only say that we have those bugs reported in the database, but others it's hard to confirm if it's a real one or not. Yeah.
Okay. Hi. For Deadlock, how do you handle condition variable?
Conditional live. What? Excuse me.
For the Deadlock, how do you handle condition variables?
Conditional
variables.
Variables?
Condition variables.
Conditional variables.
Condition variables.
Condition variables.
Yeah, for Deadlock.
Maybe we can talk about that later. Yeah.
Okay.
Sorry.
We have time for one more question if anyone has one. Otherwise, we can thank the speaker, please. We're going to switch gears now to race detection. This paper is high coverage, unbounded, sound predictive race detection. And the speaker is Jake Romer.